Hello, everyone, and welcome. Have you ever built a really big Lego castle and then stopped to think about what it's really made of? At the end of the day, it's just a whole bunch of individual little bricks, right? Well, numbers are a lot like that. A big number might seem complicated, but it's actually just built from smaller, simpler pieces. Today, we're going to be number detectives, and we're going to find the secret building blocks that make up every single number out there. Yep, that's right. Every single whole number is either one of these special building blocks, or it's made by multiplying those blocks together. Think about it. You don't build a Lego castle by adding bricks. You have to connect them, right? Well, with numbers, our connection tool is multiplication. So our mission, should we choose to accept it, is to find the most basic, fundamental bricks in the entire number world. So that leads us to the big question. If we keep taking apart that Lego castle, piece by piece, we eventually get down to the individual bricks. The ones that you just can't break down any further. So what are the unbreakable bricks of numbers? Let's figure that out. So what are these building blocks even called? Well, they're called prime numbers. And to really get what makes a number prime, we're going to do a fun little activity with some cards. It's going to show us a super important difference between different kinds of numbers. Okay, take a look here. Imagine you have 6 cards. See how we can arrange them into a couple of different rectangles? We can make a long, skinny one that's a 1 by 6, or we can make a 2 by 3 rectangle. So that gives us 2 different ways. Now, what about 7 cards? Try to picture it. No matter what you do, you can only make one long rectangle, a 1 by 7. There's only one way. And this little difference, well, it's the key to everything. So what's this really telling us? The numbers that make up the sides of our rectangles, we call those factors. For the number 6, its factors are 1, 2, 3, and 6. But look at 7. The only factors it has are 1 and 7. It has exactly 2 factors, just 1 and itself. This special property, this is what we've been looking for. And that gives us the official name. A number like 7 is called a prime number. Just like it says here, a prime number is any number bigger than 1 that has only 2 factors, 1 and itself. Numbers like 2, 3, 5, and 7 are all prime. These are our basic Lego bricks. They're the simplest pieces. So what do we call numbers like 6 then? Those are called composite numbers. A composite number is just any number bigger than 1 that is not prime. It means it has more than 2 factors, and you can build it by multiplying smaller numbers. Like 6 is built from 2 times 3. So these are our castles that are made from our prime number bricks. Now, we're about to start breaking down some really big numbers. And sometimes we're going to find that we use the same prime brick over and over again. To save ourselves from writing things like 2 times 2 times 2 times 2, mathematicians came up with a really cool shortcut. It's called an exponent. Let's look at this example right here. We read this as 5 to the power of 3. The big number on the bottom, the 5, we call that the base. That's the number we're actually multiplying. And that little number up top, the 3, that's the exponent. All it does is tell us how many times to multiply the base by itself. So 5 to the power of 3 just means 5 times 5 times 5. See? It's just a shortcut. Let's walk through one together. How would we figure out 2 to the power of 4? Well, step 1, the base is 2. Easy enough. Step 2, the exponent is 4. So step 3 tells us what to do. We write out the number 2 4 times with multiplication signs in between. And for our last step, we just do the math. 2 times 2 is 4, times 2 is 8, and times 2 again is 16. So 2 to the power of 4 is just a much faster, neater way of writing 16. Okay, it is time for the main event. We've got our prime number bricks, we've got our exponent shortcut. Now we can put it all together to break down any composite number into its most basic parts. And this whole process has a name. It's called prime factorization. The best way to learn this is just to do it. And we're going to use a really fun tool called a factor tree. It helps us find all those prime bricks. We'll start with a simple number, 12. Our mission, find the prime numbers that multiply together to give us 12. So, just like it says, we start by writing 12 at the top. Now, for step 2, we just need to think of any 2 numbers that multiply to make 12. You could use 3 and 4, but let's just go with 2 and 6. So we draw 2 little branches coming down from 12, and we put a 2 at the end of one and a 6 at the end of the other. Okay, now we look at the numbers at the ends of our branches. Let's start with the 2. Is 2 a prime number? Let's think. Yep. Its only factors are 1 and 2.
So because it's prime, this branch is done. We can't break it down anymore. So we'll just circle it to show that we're finished with this little part. All right, let's look at our other branch now, the one with the number 6. Is 6 prime? Nope, we already know we can break that one down. So step 2, what two numbers multiply to get 6? Easy peasy, 2 and 3. So we draw 2 new branches down from the 6. And for our last step, we check our new numbers. Is 2 prime? Yes, it is. Is 3 prime? Yes, that one is too. So we circle them both. And look at that. Our factor tree is all done because every single branch ends with a circled prime number. Now, all we have to do is collect all those circled numbers. These are the prime factors of 12. We've got a 2, another 2, and a 3.
Now, for the final step, let's write our answer out nice and neat. We have 2 2's being multiplied together. Remember that shortcut we learned? We can write that as 2 to the power of 2. And we also have that 3. So the prime factorization of 12 is 2 squared times 3. How cool is that? We've just found the unique prime DNA for the number 12. That was great. Now that you've seen how it's done, let's practice with a slightly bigger number. Let's try 60. Okay, now it's your turn. What do you think the prime factorization of 60 is? This is a great time to pause the video, grab a piece of paper, and try to draw your own factor tree. And remember, it doesn't matter how you start. You could do 6 and 10 or 2 and 30. You'll always get the same final answer. Go on, give it a shot. Ready to check your work? Let's see how you did. Let's say we started our tree with 6 times 10. Okay, step 2, we break down the 6 into 2 times 3. Hey, both 2 and 3 are prime, so we can circle those. Step 3, now we break down the 10 into 2 times 5. And look at that. 2 and 5 are also both prime. So for step 4, we just collect all the circled prime numbers we found. A 2, a 3, another 2, and a 5. And finally, let's write out our answer using those handy exponents. We have 2 2's, so we'll write that as 2 squared. Then we just multiply by our other primes, the 3 and the 5. So the prime factorization of 60 is 2 squared times 3 times 5. Case closed. If you got that right, you are officially a prime factor detective. Fantastic work. So let's do a quick recap of our adventure today, shall we? We learned that prime numbers are kind of like the basic Lego bricks of all the numbers. Then we have composite numbers, which are the bigger things we build with those bricks. We learned about a great shortcut called exponents. And finally, we used prime factorization with our factor trees to break any number down into its own unique set of prime parts. And before you go, here's a really cool thought to leave you with. Prime numbers aren't just for math class, you know. They're actually out there in the real world. Did you know that some animals, like cicadas, use prime numbers to literally survive? Some types spend 13 or even 17 years underground before they all come out at once. Well, 13 and 17 are both prime numbers. Scientists think this helps them avoid predators that might have life cycles of 2, 4, or 6 years. It's an amazing example of math in nature. Thanks so much for being a number detective with me today.